Okay. So I was stuck somewhere and I missed something. So I will just prove it here. So the other one is assignment. So we are proving the following. We have so theorem. Okay, if is it fine? Can you hear me?
Yes, sir.
Okay, good. So we want to prove the following. We took the trace class operators. Okay, B1 H star. We were proving the following. B1 H star equal to P of H. Okay, that's what we want, right? So if you have a T, if you have a S in B of H, then we define psi S of T, base of Ts, right? For all T in B of H. We want to prove that this gives an isometric isomorphism between the dual of this. Okay. So we prove the following. So this is equal to this. That's what we want to prove through this linear function. Okay. So whatever that. Okay. So we proved one way. So given anything, we have proved that this gives a linear functional. We proved the following. Given S in G of H, this is bounded. We have proved that chi st mod of this equal to trace of Ts. This is less than or equal to. So which is the S is the norm and trace of mod. So this implies. So she pointed out that I had made a mistake in the earlier proof. So in the earlier proof, there I said if you have a P, then I said norm P is less than or equal to some. Yes, it should be norm P1. I mean, in the notes where I have, this is what if you go through it, it will be, I mean, it's just a mistake. Instead of norm S, I wrote instead of norm T, I wrote norm S. Yeah. So that you have to notice. It's a silly thing. Okay, so here, so we have proved that this implies norm of chi is less than or equal to norm of S. We have to prove the other way. So we have to prove the other way. So for that, so I will erase it and do it here, okay? Because I will not. So to prove the other way, suppose chi is some linear function. This, okay? Then you define the following. Define a bilinear form. P of xy equal to chi of txy. And txy is the rank one operator which we have defined. Okay. So we have verified that txy. I have verified this txy, tx prime, y prime equal to, you will get the inner product of so x prime, y, x y, right? So this I have verified. So I erase this and try to write it. Shall I erase the whole thing? Is that okay? I mean, these things are already in the notes and video. So I will partition this board and then do it. Okay. So we have defined. So this is for all xy in. We want to prove that this is a bounded sesquilinear form. So if you take mod of dxy, okay, that is equal to so chi of dxy. You don't see?
So can you make it? Yeah, it's okay now. So
chi of dxy. Now this is less than or equal to norm chi times this. This is the norm t of txy1. Okay. So which is just the trace. So that is equal to norm chi trace of txy star txy. So this is just the one norm. Okay. Okay, if you want. So okay, what I have written is the norm. Okay, this is what we want. Now Txy star Txy is equal to T norm x square times Tyy. So if you want, you can write it as Tyy, yeah, Tyy, correct. So that is equal to norm x square, norm y square. You just verify this. T of y by norm y by norm. I mean, to make it unit vector. So now for any unit vector, E H, okay, TEE square root is equal to T. You just verify TEE, so you just want TEE star TEE, okay, acting on TEE star is equal to TEE, TEE square if you want. So TEE acting on some Z equal to ZEE. And if you apply TEE on that, you will get the same thing, right? Because norm E square equal to 1. This is equal to, if you apply it again, EE, again Z. Just apply the definition, you will get that its square root is this. So that implies that whatever we have here, so Txy star Txy power half is actually equal to norm x times norm y times Ty by norm y by norm y. Okay. Now you just, for any such thing, trace of TEE equal to 1 for all unit vector. This we have already verified, because TEE, you act it on EE, and you take an orthonormal basis with that's all, equal to 1. That you just verify this. Take an orthonormal basis with E1 equal to E, okay, and then EN whatever the summation is equal to just, I mean, whatever so all these things imply that, so this is our Bxy, whatever I have written here, mod of this is less than or equal to norm phi times norm x. I mean, I had a square there, so norm. So this is a bilinear form. This is a bounded bilinear form. Okay. So I hope this is okay. So this implies there exists a S. So if you have a bounded bilinear form satisfying this, you apply twice the Riesel lemma. Okay. So there exists a S in B of x. That's that B of xy equal to Sxy. So now this is true for all rank 1 operators. B of xy equal to, so this implies, so let us forget about B now. B is not needed anymore. So this implies there exists a S in B of x. This is what we have. Okay, such that phi of T xy equal to trace of I mean, it's same as this, trace of STH. Same thing, both are same. Okay, if you go through the same idea, this is same. Okay, verify this. So now, if T is self-adjoint, in particular, it is normal. Okay. But, then T is equal to summation lambda n, and T is trace class. Okay, T is in B1. Trace class, so it is compact. So T of lambda n will look like TEN, right? That is any problem? Here, summation TEN okay, is equal to, I take an orthonormal basis starting with E. First element is E. So which is equal to TE. Everything else TEE. Okay, I have written it correctly. I was went very fast. TEE is an operator, rank 1 operator, acting on E taking inner product with. Okay. I mean, this thing should be good exercise. I mean, I just went through it. Okay. T is too many E's. TE is an operator. Acting on E, you will get 1. That's all. Okay. That's all. So any self, am I going fast? Yes. Because you are there. Okay. So you should tell me in the. Anyway, this was the confusion. The other one is you want to leave. Huh? Okay. So I will give the assignment next one. This finishes the whole thing. So now any self-adjoint operator you can like this. This is just spectral theorem for compact operators. Okay. This is just TEN equal to lambda n. Okay. So it's exactly that. Right? You just check. I have just written it in a different notation. That's all. It's the same thing. Okay. The same thing I have done. Any T is normal, so it will look like that. So this implies trace of T. Trace of chi of T you want to find, which is equal to chi is continuous, so you can take it inside all those things. Okay, you can take it inside. I don't want to write all that. So chi of T en en. Okay, so this implies chi of lambda n. So T en en. So this is just going to be there. What you have? Yes, E n e n. Right. Okay. Now that is equal to summation lambda n. You can take it inside. If you want, you take it here or take it there, whatever. So which is just STENEN summation, which is just equal to traces. That's all. It's directly, which is equal to traces. And this is what we want to do. This is for self-adjoint operator. Now any operator can be written as linear combination of two self-adjoint operators, which you know from matrix theory. Okay. So any T in B of H, in case we don't have done that, T is equal to T plus T star by 2, right? T plus T star by 2 into 1 by 2i minus T star. Is that right? What I have done? Yeah. Okay. So that's all. So any these are two self-adjoint operator apply to this self-adjoint. That's all. So if this is clear, what I was talking as assignment, I will talk about that. Unfortunately, if I have another table here, otherwise I have to move it here. So can I move the table?
Yes, yes, sir.
Yeah. This is the question. Okay, I will write here so that I don't have to erase that. So this is the assignment. So have you copied? Done? So the assignment is the following. So this is the proof. I will orally give you the proof anyway. The idea. Prove that E and B are orthogonal basis for H. Prove that T, E, N, E, M. N by M. So this is an orthogonal basis for the Hilbert-Smith operator, the Hilbert-Smith norm. Okay, so what do you have to prove? You have to prove that two things: trace of T, E, N, E, M star T, E, N, E, M is equal to E, N prime, M prime equal to N, N prime. You just evaluate it, you will get it. What we have done, you evaluate through En or Em, whatever one of them. It doesn't matter. If it is En, you can take it the other side and trace you can do that. So it is just direct calculation, which I partially did in the last class. Okay. So from that, it will follow that they are ortho normal set. Okay, and they all have norm 1. If you compute the trace of these things, Tn star this T, take the trace that will have trace 1. So it's an orthonormal set, you can directly verify. So the rest is you have to verify that it's a basis. It's a complete orthonormality. It's a complete basis. So for that, you compute this. What do you have to compute? So you take the inner product, trace inner product. This is a Hilbert-Smith inner product of E, E, and E. You compute this. This is equal to, so this is Hilbert-Smith inner product. Okay. So can you see? Anyway, after I move, you can see. So this is equal to trace of E, En, Em, T star. I mean, if you want, you can use S. Okay, the T is not confusing. So T, En, Em. Now this is equal to summation trace T star or whatever. So you can take the. Did I? Huh? Say it again. You want to put star here and then this. So whatever. I mean, there may be a star, there may not. It doesn't matter. You will finally. So the thing is, you have T, En, Em, and there is a T star. Then you can evaluate it in Em. So you can put it here if you want. Okay, that doesn't matter. Then you can use it some En, Em. Okay. Then if you apply this, you will get n should be equal to n should be equal to m or something. Whatever, you verify this calculation. Finally, you will just get Em. Okay. This is what is called matrix form. I mean, in a finite dimensional, any operator is given by a matrix, where the entries of the matrix are this in finite dimension. In infinite dimension, it's straight, just an infinite matrix. That's all. Okay. So this determines the operator. This implies E, En, Em equal to 0 in the Hilbert-Smith operator is equivalent to saying T, En equals 0. Okay, which is equivalent to saying T is 0. That is what we want. That means it's an orthonormal. That's all. So I have given the proof, but you have copied also. But you can, if there is something to verify, that's all. I have almost given all the proof. Okay, but still write it as an assignment. Okay. Yes, for all of them. The matrix entries are 0. That's all. So the operator should be 0. Or you can use orthonormal basis to verify. So this is slightly, so maybe I'll write here. You have copied the assignment. Anyway, it's recorded. So this is the assignment 2. So you take H equal to L2. X is a nice. Is nice about it. Maybe you can even take compact space or whatever. I don't know. So X. Then consider the
So I'm not able to see the first we are writing. I think because of the light. What is that H equal to something?
Yeah, if I put up the light, you won't see anything. So I will tell you that it's just L2 X mu. Hilbert space L2 X mu. That's all I have written. Okay. So here I'm going to write it again. The same thing with a product, of course. L2 X mu cross L2 X mu. I mean, not X. Sorry. I mean, it should be what is called a tensor product, but still, since I mean, this is exactly what you will see what is tensor product. Okay, but this is X cross. Maybe I write it like X2 mu. You know this product measure. Okay, just the product measure on X cross X. Okay, this is you take a function, 2 variable function, then you define Tk acting on any f equal to integral over x k of xy of y d. You integrate it in the second derivative. So first verify that this is the assignment. First verify Tk is bounded. And just quickly give a proof. Maybe I will say it over. You want to check whether this is just the inner product. You fix a x and then write it as a function in y. This is just the inner product of that function with f, right? That's what it is. Maybe put a bar somewhere. Okay, there's a bar needed. Okay. Then if you take another function, if you want to take something like this, tfg it will be just this function equal to k of fg. Let me call what is f tens rg. Where f tens rg is a function of xy equal to f of y g of y. Okay. This is just the definition. Tk f fact. No. Tk
Sir, tensor is f of x g of y, right?
f of x g of y. Yeah.
F of x g of y.
Y only I have written. Yeah.
Y first is f of x.
Correct. F of x g of y. Okay. Now this is just the inner product. Okay. So you can verify this. Now what you do is this L2. See, these kind of functions generate the x2, c of x2, and then I mean, see this f of f tensor g. This kind of functions. You take these functions and span of this. I mean, take the linear span of these things. That will be dense in the c of x2 by Stone-Weierstrass theorem. Okay. Now using Stone-Weierstrass theorem, if you apply the Lebesgue-dominated convergence theorem, you will see that that is actually dense in L2. This was some similar problem was there in the exam. Okay, similar problem. Okay, you have to use Lebesgue. See, this is dense in this means what it's dense in uniform now. Something convergence in uniform now, then you can take the limit inside the Lebesgue integral. So you have to use that to prove that this kind of functions, not this kind of function. This is total. I mean, linear combination of this kind of functions is dense in L2. Okay. So yeah. So from that, I want you to conclude that. So what is the assignment? I haven't said. So verify dk is bounded. From this, you can verify dk is bounded from somewhere. Okay. So I mean, you can verify that norm tk is less than or equal to norm k L2. Okay. This you can verify just by this inner product. You can remove it and put a f two variable function. Okay. I mean, I'm not giving the whole full proof. Okay. From this, you can verify this. So now this is the assignment, actual assignment. There exists a unitary operator u from this L2 x2, this kind of function mu to all Hilbert-Smith operator. Right? K going to T. This is what this is. So I tell you the proof. So now you know that f tensor G is total. I mean, the linear combination of those things are dense in L2x. In particular, if you take an orthonormal basis for L2x, an orthonormal basis, then EI tensor EJ, that will form an orthonormal basis. So this is the proof. EN is an orthonormal basis for L2x. Okay. Then En tensor EM, this kind of product thing. Okay, with NM is an orthonormal with N and M varying. This is orthonormal basis for the product. You can prove this. Okay. Once you prove this, then it is just from the earlier assignment, it will follow immediately. A unitary operator is just something which takes orthonormal basis to orthonormal basis. You take this, these are functions, right? En is an orthonormal basis for L2x. So you take this kind of function, this will map to Ten, Em, which are actually dense in the Hilbert-Smith operator. You just write down everything, it will follow that this unitary operators. This implies that every Hilbert-Smith operator on this space looks like this. And you can also prove that the Hilbert-Smith norm is exactly equal to this. That is a unitary operator. So in particular, maybe I will write it there. So this is the final statement, which is just, I mean, same thing written in a different language. Okay. If you prove that unitary, then it follows that this is true. Every Hilbert-Smith operator on L2x is given by, I mean, unique, all those things. I mean, there is a unique one-to-one correspondence between Hilbert-Smith operator. Given a K, this is a Hilbert-Smith operator. Given a Hilbert-Smith operator, there exists a K. Given a K in L2 X cross X, X2. Okay. By the prescription, by K going to TK. So this is what I wanted to do in the last class. Yeah, it's fine. So, okay. Thank you. Okay. So if you have any doubt on this or earlier, you can ask. So since no discussion is happening, I will stop recording. Okay.